Electrical potential energy stored in a capacitor. We know the work done to bring a unit charge from one point to another is potential difference between them. Then work done to bring a charge dq is dw equals work done to bring unit charge into the bringing charge, that is bq. So we can write dw equals v into dq. Since v equals q by c, dw equals q by c into dq. Then total work done to bring all charge is w equals integral dw equals integral q by c dq. Since c, that is capacitance, it is a proportionality constant, so take outside. So w equals 1 by c integral q dq. But the integral of q dq is q square by 2. So total work done w equals 1 by c q square by 2. When q is replaced by c into v, the work done becomes half c square v square divided by c. After cancelling c, work done equals 1 by 2 cv square. When we are replacing c equals q by v, the expression becomes half q by v into v square. That equals half q into v. Since the total work done to store total charge is converting as the total potential energy, the total potential energy stored in a capacitor is U equals half q square by c or half cv square or half q into v. Energy density of electric field in the capacitor. We know the total potential energy stored in a capacitor is U equals half q square by c. But q equal to sigma a and sigma equals epsilon 0 into E. That is q equals epsilon 0 E into A. Also, the capacitance of a parallel plate capacitor is C equals A epsilon 0 divided by D. When we are replacing Q by epsilon 0 EA and C by A epsilon 0 by D, U equals half epsilon 0 EA whole square divided by A epsilon 0 by D. After rearranging and cancelling, we will get potential energy, that is total potential energy stored in a capacitor capital U equals half epsilon 0 E square AD. But potential energy density means potential energy per unit volume equals total potential energy divided by total volume. Thus, small letter u equals capital U divided by V. Now, substituting the expressions of capital U as well as V, we will get small u equals half epsilon 0 E square AD divided by AD. So, potential energy density stored in the capacitor is small letter u equals half epsilon 0 E square. Loss of energy on charging a capacitor. If first capacitor C1 is connected to a battery of potential difference V1 and second capacitor C2 is connected to a battery of potential difference V2. Then the initial total potential energy stored in the capacitor is Ui equals half C1 V1 square plus half C2 V2 square. When these two capacitors of different potentials are connected, charge will flow till both potentials are same. So they attain a common potential which is Vc equals total charge by total capacitance. That is Q1 plus Q2 divided by C1 plus C2. But we know Q equals C into V. That's why the expression becomes C1 V1 plus C2 V2 divided by C1 plus C2. After connecting them, both will attain common potential V. So, final potential energy is UF equals half C1 plus C2 into V square. Substitute the value of V square means common potential. It is also Vc. Then the expression becomes half C1 plus C2 inside the bracket C1 V1 plus C2 V2 divided by C1 plus C2 whole square. If first capacitor C1 is connected to a battery of potential difference V1 and second capacitor C2 is connected to a battery of potential difference V2, then the initial total potential energy stored in the capacitor is Ui equals half C1 V1 square plus half C2 V2 square. When these two capacitors of different potentials are connected together, charge will flow till the both potentials are equal. So they attain a common potential called Vc, which equals total charge divided by total capacitance. Means Q1 plus Q2 divided by C1 plus C2. Since Q equals CV, expression becomes C1 V1 plus C2 V2 all divided by C1 plus C2. So the final potential energy of two capacitors together is UF equals half C1 plus C2 into Vc square, which equals half C1 plus C2. Now we are substituting for Vc. That's why C1 V1 plus C2 V2 divided by C1 plus C2 whole square. After cancelling C1 plus C2, expression becomes half C1 V1 plus C2 V2 whole square divided by C1 plus C2. During this flow of charges through the wires, there will be some energy loss in the form of heat. So the expression for energy loss is Ui minus Uf, which equals half C1 C2 divided by C1 plus C2 inside the bracket V1 minus V2 whole square.